dear American Geophysical Union members and associates, dear colleagues, friends, and guests. Welcome to the 2020 Gutenberg Lecture from the Australian Academy of Sciences' beautiful Shine Dome in Canberra, the nation's capital. This year's recipient of the Gutenberg Lecture is Professor Malcolm Sambridge. The lecture itself is presented annually in recognition of the outstanding contributions to the field of seismology. And I'm Hrvoje Tkalčić, one of Malcolm's colleagues from the Australian National University, and it's my great honor and pleasure to introduce Malcolm to you today. So Malcolm comes originally from the United Kingdom, and his educational background is in physics and mathematics. He received his PhD in geophysics in 1988 from the Australian National University, and he was then a fellow in the Carnegie Institute of Washington between 1988 and 1989. Subsequently, he was a research associate at the University of Cambridge between 1989 and 1992, the year he returned to Research School of Earth Sciences at the Australian National University. And here, as you all know, he has had a fruitful academic career with nearly 150 international peer-reviewed papers. So Malcolm, before I go any further, I would say that among other recognitions, he received the Prize Medal from the Royal Astronomical Society, London, in 2009. He was elected an AGU Fellow in 2010, elected a Fellow of the Australian Academy of Science in 2015, and last but not least, he, apart from this Gutenberg Lecture, he is the recipient of the 2021 Benno Gutenberg Medal that is awarded by the European Geosciences Union. Malcolm is among the leading mathematical geophysicists in the world. His innovative contributions to inverse theory, most notably Monte Carlo methods, but apart from Monte Carlo methods, as I'm sure you will see in this lecture, other innovative methods have really shaped the field of seismology and influenced other disciplines. And not just through his outstanding research contributions, but also through his willingness to share knowledge and methods through an open source software, through his drive to educate youngsters in his leadership role in the Seismometers in Schools initiative. He has made a significant and long-term impact. So for all that he has done, he is an incredibly well-deserving recipient of this award. So Malcolm, please give a warm welcome to Malcolm.
So, thank you very much, Hrvoje, and thank you all for coming along today on this beautiful Thursday summer day in Canberra. So, the title of my talk today has two important words in it: bias and tour. It's a biased tour, and a tour is not complete without, let's see if it works, tour guides. Now, it's appropriate at this sort of time to acknowledge one's own tour guides, and these are all people that I've benefited from very much over the years who have taught me and helped me along the way. I won't tell a story about each of them because it will be taking up the whole time of the lecture. But at the bottom there are some particular people who have contributed directly to this talk: Matthias, Busa, and Andrew, who are in the audience. The most recent slide came in at 12:01 today, and it made it into the talk. So thank you, Matthias, for that one. And while we're doing our thanks, let's thank our sponsors. We have to thank our sponsors for various organisations: the ANU, CSIRO, Audscope, Geoscience Australia, the Australian Research Council. All have contributed funding or in-kind support for infrastructure or research in one way or another, the things you're hearing about today. And one that you would not be familiar with necessarily is InLab, which is a new venture, collaborative venture between CSIRO and ANU that we've just started, and they're supporting the drinks later, so we've got to acknowledge them too. This lecture is named after Bino Gutenberg, and here's a picture given to me by Andrew and Brian. It came out of a discussion where Bino Gutenberg is the person highlighted in the figure. This is 1929, photo taken at the Caltech World Authorities at the Seismo Lab, and there are some absolutely ground-shaking names of people in this. There's Gutenberg, as you see, Benioff to his right, there's Charles Richter in there, Wood and Anderson, Harry Reid, Arthur Day, but the person directly to the left of Bino Gutenberg is Sir Harold Jeffreys, and by way of a connection, Harold Jeffreys connects to my own lineage, of an academic lineage. He would be technically my great-grandfather from academic terms, and is also connected to Andrew and Brian. So we keep it all in the family. But anyway, there's Bino Gutenberg. Now, the title of the talk is A Biased Tour. Now, biased meaning having a preference for one thing over another, and I'll certainly have that, because this is not intended to be an unbiased, balanced review of geophysical inversion. It's very much a bias because it's my outlook. And it's a tour in that we'll be stopping by a number of places. Not for very long, but we will visit them. And in doing so, it's also an AGU talk. And everyone knows that you write an abstract for AGU, and your talk doesn't necessarily correspond to your abstract. So my prior was to talk about the past and the present of geophysical inversion. But actually what I'm going to talk about is the present and what I see as the future, my biased view of the future. And indeed, this talk is really aimed at students and postdocs, because it is some seeds of ideas that I think that will be influential or potentially influential in the future of geophysical inversion. Now, it's a dynamic talk, at least in one way, which is that there's a website with everything you can see here today, all animations on that website. Thank you, Andrew. And the idea is that you can give some feedback. If you don't ask a question now, you can ask one later. You can complain. You can say, that was very biased. You can engage. And the idea is to sort of create that dynamism. So please give some feedback. Agree, disagree. Suggest some ideas. Okay, so inverse problems is something I've studied for a long time, had a lot of interest in, and they come in all shapes and sizes. From geoscientists are often looking at inverse problems in the sense of we have indirect information about the Earth. Yeah? Most of us live on the Earth, and we measure on and above the Earth, and we're interested in things that happen at depth or sometimes even in the past. So seismic imaging, using seismology to look at the Earth's interior at small scale lengths there, refraction seismology used for exploration geophysics, airborne geophysics. We've got Ross Brody in the audience, who's an expert on airborne AEM. We have airborne geophysics, and even new styles of inverse problem. This is a slide from Rodri Davies, which is trying to look at the thermochemical history of the Earth, bringing together multiple strands of information, including geophysical and geochemical. So all shapes and sizes, but I can't pop this slide up without reminding people my favourite quote from Samuel Carlin, that the purpose of models is not to fit the data, but to sharpen the questions. Yet, we mainly build models. The purpose is actually to try and create understanding of the Earth. Now, here's some very famous pictures of people who have created models. Over 30 years of seismic imaging, from the ones on the top left here, the sort of classic papers by Zawonsky and Woodhouse, who brought together a number of earlier studies, producing the really first generation of seismic image of the whole Earth. Very long wavelength, and in the day then, it was sort of 2,000 surface wave seismograms, 1,500 body wave seismograms, and 870 source receiver pairs. Fast forward 30 years, and this topic has moved on to something like Ebru Bodzag's here work on the very first generation of global tomographic model from adjoint tomography, where they're now using 1.2 to 3.8 million pieces of data and taking something like 1.6 million CPU hours to create these 15 iterations of this model here. So enormous changes in data volumes and computational resources. But there's one thing that hasn't really changed between this study and this study, and that's how we fit our data, how we define the objective of an inversion. Typically, we're doing some sort of minimization of squares of residuals, a least squares approach. And it's appropriate in this type of problem, and really it has not changed very much, even though the style and the process changed dramatically over 30 years. So, today I'm going to be talking about things that challenge that notion of least squares, and pointing out a few other ideas that I think are very valuable that could be useful in the future. Now, here's a topic I've talked about before, compressed sensing, and it's really by way of introduction to the next few slides. So compressed sensing is a field that really has its origins about 15 years ago in the work of Kanders and Donahoe and company, mathematical scientists, and they found that you can irregularly sample data, in short, and reconstruct it exactly using an inverse method under very special conditions, but still reasonably general. And the idea is that rather than collecting uniform data that we do regularly, collect it irregularly, and provided certain conditions that we won't go into are satisfied, you can reconstruct data exactly. And their idea was, well, don't collect all the data, collect it irregularly and combine it with mathematical optimization and call that your data collection. And in doing so, you can vastly reduce the amount of storage and increase the bandwidth of data, essentially better forms of data collection. And Felix Herrmann's really been the leader of this in the geosciences, and he's convinced oil companies to sort of invest in this type of technology. And because you can do that in time series, you can also do it with images. There's an image by Escher, where it's been sampled at roughly 10% and reconstructed in a sparse sense. Now, the reason I put this up here is that it's an example of sparse inversion. In fact, it's a little gem that is missing. It was previously missing in geophysical inversion, that if you've got a problem that fits into this, that is basically an empty model, you can reconstruct it exactly or very accurately using this idea of sparsity. Now, that's all well and good. A lot of geophysicists have used that idea to try and reconstruct Earth models using seismic imaging. Now, the problem is the Earth isn't necessarily sparse. Yeah? So the question is, how do you use this technology when you don't necessarily satisfy the correct conditions, which is having a representation of the Earth in such a way that only a few of the unknowns are non-zero and everything else is zero? Well, here's an example of a single pixel model. The simplest possible example I can think of, you add these 3 pixels together, you get a sparse model like this. So the theory says that you can reconstruct models like this, which are trivially simple, very accurately, because this is sparse. But this one here is also sparse. It's sparse in a different sense, a sense of a discrete cosine model. So both of these models, the theory can be applied to. But what it cannot yet be applied to is if you combine them and look at a model which perhaps has long wavelength structure, which is a smooth background here, and local structure. And that's the situation we're offering in seismology. We might have a long wavelength mantle structure, and we think we have fine scale structure in a subduction zone or near a volcanic zone or in a small region. And the idea of overcomplete tomography, which is the PhD work of Busa here, co-supervised with Andrew, is to say, can we extend these ideas to problems of this type, where given a certain number of data, can we exploit these ideas where the problem isn't sparse, but it's sparse in two bases? Can we combine them together? And it's not obvious from the maths that you can. And it turns out, I'll show you some examples now. Here's what we're going to show you is a complex figure. We're going to have a number of rays here, some experiments from Busa. Here's going to be the reconstructed overcomplete model. Here's going to be the error in the model. It's a very simple case where we know, a synthetic case where we know the error. So this is the error in the model. This is going to be the least squares solution with some sort of damping here, squared, and this is the error in the least squared. So this is also in the same parameterization. It's exactly the same parameter. The only thing we're changing is the sparsity. This model isn't sparse, but we're going to hope and try and make the sparsity idea pick out the correct two subsparses. That's the idea. And we're going to show a movie, and on the right-hand side, you're going to see the fit to the model, the closeness of the model here. The red line's going to be the least squares. The black one's going to be the sparse solution. So, thank you, Bisa. I'm going to play this here. And what you see is, boof, okay? That cliff you see is classically what you see in a compressed sensing environment. And as we reach that cliff, if anyone was noticing, this model becomes almost exact, and the least squares toddles on until there's enough data to get better and better and better. Now, that's exactly what we hope to see in this case, because it shows that you can utilize this sparse idea and the accuracy of it in problems that are not actually sparse. So it's an extension of that, and we're calling that overcomplete tomography. Okay, so that is an idea that uses non-least squares to try and recover Earth models. And we think there are a number of different applications to this, problems that have structure on more than one scale. Now, we're moving on very swiftly from our brief visit to overcomplete tomography to machine learning. Now, I've heard lots about machine learning. The number of sessions on machine learning growing at AGU is itself growing greater than linear. Now, here's the audience participation side. This is a slide from Valentine and Trompere, and we have 4 wiggles. And given there are lots of seismologists in the audience, the question is, which one's the seismogram? Who votes for the first? Second? Third? Fourth? Fourth, yes. The fourth is the seismogram. The first, of course, is the stock price. The second one is the temperature in Birmingham. I don't know what that scale is, but I think it's cold all the time there. White noise is the third one, and the fourth one is a seismogram. Now, the very point that most of you, in fact, all of you, I think Andrew got it wrong, all of you got that right, is that you have a model in your head of what a seismogram looks like. You can look at each of those and compare it to the model in your head. You're acting as a misfit function. Yeah? You've done an optimization, you've picked out the correct one. And the whole concept of machine learning is, can we capture that idea of pattern recognition that's in your head and put it into a computer and use it to drive inversion? And I think the answer emerging is yes. So this is the work of Matthias, a PhD student in the group, and he's exploited this concept of what we call a GAN. And the GAN is a standard idea from machine learning. It is essentially the competition between two things. One thing which generates dots or models in a parameter space, unknowns. These are your unknowns. This thing will generate random unknowns. And this thing over here, called the discriminator, will try and tell you whether the data from those unknowns, those models, is good or bad. And by saying that, it sees the real data and it tells this guy, I've beaten you. I can tell your predictions from your models look nothing like the data, just like you did with the 4 wiggles previously. And the idea is the competition between these two drives this guy to get better and better and better and get models that fit the data better and better and better. So it is a competition that drives the solution. And that's the main concept here that I think is very interesting. And I'm going to show you a little example of where that could be useful from Matthias's work. So here, again, a toy trivial example to show the ideas. Given the mass of the Earth, what's the density of the core and what's the radius of the core, or an idealized ball? Here's the answer. Given the mass, how it depends upon two different solid bodies in this case. So we want to find the radius of the core and the density of the core, and to do that, it's a completely underdetermined problem. We only have one piece of data. We had the mass of the Earth in this case is 16 units. And as that line goes up and down here, all of those models, an infinite number of them, fit the data equally well. Yeah? So we cannot determine, in this toy problem, the radius and the mass, the radius and the density from the mass. So we have a very nonlinear problem. It turns out we have a nonlinear problem because this is quite complex. It's not a simple Gaussian. It's a nonlinear problem. It's underdetermined, and it's the simplest possible one I can think of with one parameter. So we're going to use that as a toy. Now, what I'm going to show you here is one application of a GAN to this problem. On the left-hand side, you see a set of samples in a model space. So this is the core radius, this is the core density. Now, these have been produced by a standard Bayesian sampling, Markov chain Monte Carlo. If that means something to you, it will mean something to a lot of people in the audience. And on the right-hand side, we're going to say, this is our data for our problem. This is actually the data. And we're going to say, can we train a neural network to reproduce that distribution? Can we do that? Because if we can, it's very useful because, well, we could use this forevermore. Rather than using very expensive Markov chain Monte Carlo, or even storing all the results, we can replace the result with a trained GAN that can generate rapidly millions or trillions of possible solutions that mimic the result of a Bayesian sampling. So if we can do that, it's a good thing and it's immediately useful. And here's a simple example of trying to do that. So I'm going to play these are the samples of the GAN as it trains itself against the data. And hopefully you'll see that the red dots, after a period of time, learn and find the distribution of the black dots. And the idea is that once it's trained itself, we can then use that to sample problems or to calculate uncertainties or anything you want in a standard Bayesian approach. And I think you see there that that worked. The red dots sort of fly off and then they gradually sample the right structure. And in this problem, it's only 2 parameters, but you get the idea that the GAN can train and reproduce the Markov chain. But this is extremely rapid. It requires no more complicated physics. I mean, a neural network is very, very simple. Yeah. So once we've trained our GAN, we can use that. We don't really have to store, in this case, it's simple, but if we try and, the biggest problem, if anyone has done Markov chain Monte Carlo, is A, when does it ever end? There's an old story that you run it, you do your best job, you write your paper, you submit your paper, and then you press the button and start your Monte Carlo again, and when the reviews come back from your paper, you stop the calculation, and you've got all the results, all the answers to the reviewer's questions in the calculation you've just done. But with a GAN, we don't need to do that anymore, because if we can train GANs for general problems, we can replace the output of a Monte Carlo, and we can use them for other purposes. Okay, so the final area that I'm going to visit, and it's going to be for the remainder of this talk, is to be talking about an alternative idea that I think is going to be important in geophysical inversion. And again, it's an idea that we've borrowed from somewhere else. Brian Kennett always used to tell me that if you steal from one person, that's plagiarism. And if you steal from many, that's research. And that's what we're doing here. We're stealing from other fields. We're borrowing. And that's how science progresses. Okay, so this field is called optimal transport. And some of you would have heard about it because there have been, and I'll come across this in a minute, a number of papers in the geosciences that have made use of this. Certainly, I am nowhere near the first. I'm about 8 years late. But we're going to have some fun and look at this idea. Okay, so here you might recognize the symbols. Optimal transport comes from the 19th century. There have been 2 Fields Medals in this topic and 1 Nobel Prize since then, often on the mathematics of it. The Nobel Prize is actually in economics. That's where the mathematicians get their Nobel Prizes. On the left-hand side is an apple. I'm going to turn the apple into an orange. I'm not going to show you the maths. I'm just going to show you some animations. An apple becomes an orange. And in the middle, I'm going to turn the apple into an orange with optimal transport. Now, on the left-hand side, I'm going to use linear. So the image you see is just going to be a weighted sum of the apple and orange. And that actually is closely connected to least squares. In fact, it is the analog of least squares in here. So let's do that. And you can see what's going to happen. The green's going to fade away, and the orange will come into view. Okay? And what's happening there is really there's no connection between the 2 images, yeah? One's just going to 0, and the other one's going from 0 to maximum. Optimal transport, however, behaves rather differently. Here's the apple turning into the orange using optimal transport. Okay? There's a little bit of graphical going back in again. And really the only thing I want you to capture from here is that optimal transport is not about one image fading and another one coming back. It's about using the character of the image and transforming it in some smooth way into another image. In fact, you can do this between any 2 images. George Bush, Bill Clinton, whatever you want. Here it's very simple. Now, the reason that this is useful is that if you have a measure of way of changing A into B, you effectively have a measure of how far A is from B. And if you can tell the difference, a distance between A and B, A could be our observed seismogram and B could be our predicted seismogram, or A could be any bit of data you want to fit. There will be restrictions, and B could be your prediction from your geophysics model or your physical model. So this provides a new way of minimizing and defining inverse problems, all which depend upon a distance measure between 2 things. Okay, so I said waveforms. Here's exactly the same thing transformed into a waveform space. At the top is the linear case. So we're moving from a blue waveform to a black waveform. And the top one, you'll see, if you look at that, all that's happening is the amplitudes of one are going down and the amplitudes of the others are going up. So least squares fitting is exactly corresponds to least squares fitting, which only looks at the differences in the heights of the 2 wiggles. On the bottom, hopefully you see the mass of one wiggle going into the mass of the other wiggle. We could think of this as a pile of sand that starts off here, a shape of a whole set of pile of sands, and they move over to a set of sand piles over here on the beach. Yeah? It's moving in position and in amplitude, and that's the key thing of optimal transport, that you're not just moving in amplitude, as the top one is, we're moving in position and amplitude. Now, I haven't described how you do this, and I'll briefly skip over it, but the distance measure between where we start and where we end in this context is called the Wasserstein distance. And the Wasserstein distance is, if we think of the piles of sand, it's very simple. It's just the mass of the sand times the distance we move each parcel of sand. To generalize that, I can put the distance to a power, and we define the P-Wasserstein distance as the mass times the distance to the power of P. So the mass in this case would be like the area under the curve, and we're moving it over. Now, the whole point of optimal transport is that you do that in an optimal, it's got the word optimal in it, so what is optimized? What is optimized is, here's my starting wiggle here, that's f of x, my target is g of x, and transforming f of x exactly to g of x I form what we call a transport plan, which is just really the recipe of how much of each parcel you move from one to the other. And what's minimized, or what's optimal, is this distance, Wasserstein distance. The distance times the mass, or the mass times the distance of power. And Kantorovich in 1942 was the one who first explained this in these terms. In fact, he converted the original ideas of Monge from the 19th century to problems that actually can be solved. It wasn't really clear when this problem was first posed that there was a mathematical solution to it. And Kantorovich reformulated it into a way where it was guaranteed to have a solution. And it comes down to just simple linear programming. Ideal, because in the 1940s and 50s, linear programming took off, especially where optimizing of factories and behaviors and constrained optimization really was in its heyday in the 40s and 50s. And he showed that this was just an example of that problem. So great, we already know how to solve these problems. Unfortunately, there's a catch. And the catch is that this, while being simple and foolproof and working for any case, is extremely computationally expensive to do this for big problems. And so the whole game has been really finding different, more efficient, practical ways of solving this problem and not using linear programming. But nevertheless, this works. So we have this concept of a transport plan and moving from one source to a target. And in doing that, we find the minimal distance, which is the Wasserstein distance. Okay, so I'm moving along to bringing this back to geoscience. Here are all of the authors, probably not all of the authors, some of the authors who have been responsible for bringing this topic into the geosciences. Bjorn Enquist and company were the first to introduce it for exploration seismology, full waveform inversion in searching for oil and minerals, etc., or at least from seismic reflectivity, essentially. Metivier, the Grenoble group here, have made some wonderful contributions to this field, really taking a different approach to Enquist in terms of the computation, but the same type of problem to be solved. And there have been a number of very recent papers exploring this idea, Hedajian and Huang in gravity inversion and seismic receiver function. But really, I'd still say this topic is in its infancy, and it's a wide open space. Because each of these studies take different approaches to how you find this distance, how you solve this math problem. And particularly, one thing I've glossed over is that really optimal transport is applied to probability distributions. It's actually not transferring a wiggle to a wiggle, but really a probability distribution into another, which is really a positive function that just integrates to one. A curve, much like you saw on the previous slide here. A curve into another curve, or a surface into a surface, or a volume into a volume. But it has to be positive. And most seismograms are not positive, of course. So how do you turn a seismogram or a general thing you might want to fit into something that you can use this on? Because it only works for positive functions or particularly probability distributions. So different people have taken different methods. Now, before I go and summarize these very, very briefly, I'm going to describe now a new approach to this whole thing that Andy Jackson and Andrew Valentine and I have been taking, working on for the last sort of year or so. It's still a work in progress. And the point I want to make is that these problems are extremely difficult to solve, but actually in one dimension, they're trivial to solve. In fact, Viliani, who won the Fields Medal, pointed out, and everyone knows this, that there was an analytical solution to this problem in 1D. So if you've got a one-dimensional PDF into a one-dimensional PDF, you can solve it exactly. You don't need to do optimization. You don't need to solve a differential equation. And it turns out that if you look through the theory, and that's what we've done here, it turns out that this Wasserstein distance is just beautifully the dot product of two terms. I can dot product two vectors. The two vectors you need to dot product themselves require a sort. So for the computational scientists in the room, it's a sort plus a dot product. But it's exact. That's the point. It's exact. So if you can do it in 1D, a general problem, it's exact to use this. Only for 1D. There's only known solutions in 1D. And here's some simple experiments I did. That's the linear programming solution. The computational cost is the function of the size of the problem. This goes up more than quadratically, in fact, as a function. The green is the analytical solution. This is a zoom up here, 200, a size of 200 dot points in our PDF, and this is a 10 to the minus 4 of the computation. So we're down in this little corner here. And there's the green one, and that's the comparator Monge-Ampere solution, which is what the Enquist and co. have used. So it's blindingly obvious that if you use a one-dimensional analytical solution, you're home and hosed because it's an exact solution to this problem. But can we make use of that? I argue that we can, and I'm going to show you how to do it. Okay, so before I get there, the open question, as I mentioned, was how you make these things positive. Okay, so we won't go through the technical case, but to make something positive, you've got a wiggle like this. We want to fit the blue to the red. To make it positive, we could add a constant. People have done that. They've rejected that. There are problems with doing so, loss of convexivity. You can just take the absolute values. You could do that. There are problems with that. You could take like with like, which means you map the positive of the blue to the positive of the red, the negative of the blue to the negative of the red. You lose mass conservation, you get decorrelation associated with that. There's even a global strategy where you map the positive to the negative and the negative to the positive. People have tried every combination of these things. They all are somewhat lacking of any sort of general applicability and have problems. A great idea, a very interesting idea by Metivier and his group in 2018 was to turn this into a 2D problem. Rather than represent a waveform here in 1D, represent it as a point cloud in 2D. And that's something they call graph space OT. Now, I think that's a very interesting idea. In that case, you can get different mappings depending on what your choice of distance is, etc. I won't go into the details of this, but suffice it to say it's still an open issue. But this idea here is a sort of forerunner into the thing we're going to present, which is this one. So here's a waveform. It's actually a receiver function. And step one of the approach I'm going to propose here is to say, let's turn this wiggle into a two-dimensional image. And here's my two-dimensional image. I'm going to take all the points on the plane that are closest to any one point on the wiggle, on the seismogram, and call that the distance to the seismogram, the nearest distance of all the points on the seismogram. I'm going to associate that with a point on the plane. So I calculate a nearest distance field around the seismogram. So it's 0 on the seismogram and moves away. Now, seismologists will immediately recognize this calculation because it's exactly the same as wavefront propagation in a seismic model. Yeah? Very, very familiar. We're treating the seismogram as our wavefront and propagating it north and south at a constant velocity. So this is actually quite simple to do. Sethian introduced something called the fast marching method to do this. Nick Rawlinson exploited that in a series of papers and produced some nice ways of generalizing that. This is a very familiar calculation. So I'm going to go from 1D to 2D. And step 2 is going to be, well, in step 1 here, I've got a function which is 0 on the wavefront and increases away. And really, I'd like it the other way around here. I'd like it to be maximum on the wavefront and decrease away. So what do? The simplest thing to do is put it to a power of e. Take the exponential. So here's my PDF of my seismogram. It's a maximum on the seismogram, and because I've just simply taken the exponential and I've generalized it by putting it over a lambda, this is a fiddle factor. It's going to be my fiddle factor. I create a two-dimensional distribution around a wavefront. Now, I love these pictures. This is going to be my object that I'll compare between the observation and the synthetic. Now, I have to make a choice of a lambda, so there certainly is a fiddle factor there. But I told you that two-dimensional Wasserstein calculations are quite difficult, and I really would like to avoid them. So I'm now going to take a shortcut, and here's my shortcut. I want to compare this sort of fingerprint. I'm calling it a fingerprint. Fingerprints have been used multiple times in the geosciences recently. I think Hivoya used them in a paper. I think that looks like a fingerprint, so I'm going to claim the fingerprint space and call this my seismogram fingerprint. Here, it's just 2 Ricker wavelets. So comparing this to this, remember it's e to the power, I'm just going to take what we call the marginal, the marginal, I'm going to integrate that function over the amplitude to produce this blue curve here. So that's my observed, that's my predicted, and I'll integrate it in the opposite direction. That way is over time, integrating over amplitude this way to produce 2 marginals here. So now, I've taken it's an approximation, but I'm going to take, rather than comparing the entire 2D image, which is possible to do, it's just a bit slow, it's possible to do, I'm going to compare 2 one-dimensional Wassersteins. I'll calculate the Wasserstein between here and here and here and here and just add them together. Okay? So putting that all together, that has some big advantages in this because essentially a technical reason that the computational cost doesn't scale as a power of the size of the seismogram. It goes as n rather than n squared, essentially. So that's very nice because as these things get bigger and more complex, your thing hasn't run off and taken your entire computer budget. So this is very efficient. We put it all together, we have a set of boxes here. So we start off with an Earth model. Whatever problem you're dealing with, it produces a waveform. This is plug and play. You could put some other problem in here. These are the things we'd like to know from the waveform. Here's got our waveform. From our waveform, we get our fingerprint, which is actually a fast marching calculation, efficient, simple. From the fingerprint, we get our PDF, as shown here, which is, again, an analytical expression. And from here, we take the optimal transport between the observed PDF and the synthetic PDF. And that can be done very efficiently with the marginal idea I just described. Now, this is all fitting together. The whole point I've made these decisions is to fit them together to make them simple. I'm going to end with an example on this, just to show that it works, at least with our simple, a simple example that shows it works with this new concept of a PDF from a fingerprint. Now, here's my little fitting problem. I just made this up just to illustrate the ideas, that's all. So I have a predicted, in this case it's a double Ricker wavelet. There's my predicted, that's the starting point. So this is time, amplitude, and here's my observed. And I want the blue to fit the orange. Well, it can change in time, of course. The blue can slide backwards and forwards, yeah? So that's a phase change or a shift. That's one way we can change this model. It could change in amplitude. Here it's a smaller one, that's another way. And it can change in frequency. So my 3 unknowns in this problem, in this simple little problem, are just frequency, amplitude, and time shift. And those are the sort of things that you need to fit to make a waveform fitting process work, yeah? But here I'm directly fitting them, so it's quite simple. So to give you an idea of least squares versus Wasserstein, on the top of this figure, I'm going to show an animation now, and we're going to slide the blue over the orange. And the middle, the red dot, is going to be, in the next pictures here, the 2 red dots is going to be where we are according to an L2 misfit, the least squares difference, and where we are according to the Wasserstein. You can see what's going to happen. As we slide one over, the L2 misfit gets better and worse and better and worse, of course, as things line up and get better and worse and better and worse. And that's what creates nonlinearity. That's called cycle skipping. It's a well-known problem in exploration geophysics, but also in fitting any high-frequency seismogram. So I've taken this example, I've sort of expanded it from one presented by Enquist and Flores in 2014. But you can see, beautifully, the Wasserstein distance is perfectly quadratic. Beauty. We can optimize this a lot easier than we can optimize that. In 1D, it's trivial, but you see the idea. So, let's turn it into 2D. This is the time shift we've just seen here for this fitting problem, and that's the amplitude. And this is the surface of the L2 misfit. And the red dash is the global minimum. So if we were doing this from an inversion point, we might have our 2 unknowns here, amplitude and time shift. We've got to jump over these barriers to find our way to the global minimum. And that's a classic multi-minimum optimization problem. That's where all the problems occur. All right? So what does the Wasserstein surface look like for this problem? And I said you could have the mass to the power of, the distance to the power of p. So we're going to look at a p equals 1 and a p equals 2. What's the surface going to look like? Here we are. For p equals 2, it's perfectly quadratic for this problem. And for p equals 1, it's a simple linear surface here. On the bottom here, we've got our contours. And we can see, interestingly, that the global minimum of the quadratic surface is not exactly at, because there's noise in the problem, but it's very close to the true global minimum of the best fit, or of the true model. But all we seek is the global minimum. The global minimum of this is at the same point as the global minimum of that in this problem. So optimization procedures presumably will work much better. We're very encouraged by this. This is what we want to see. Turning a multi-minimid surface into a smooth quadratic surface. So let's try and optimize it. Well, skipping over very quickly, we can put this into an optimization framework. Anyone who's done this will say, but you've got to calculate derivatives. So it's worth just mentioning that in any optimization framework for this, with these our colored boxes again, it turns out that once we get to our waveform, what we want is the differential of the Wasserstein with respect to our model parameters, and we can stick that together using the standard chain rule. And the point is, all the hard work's done with my pencil and paper, working out the derivatives. Each of these derivatives are analytical. I'll say that again. Each of these derivatives are analytical. We don't have to do any calculation, no solving of a differential equation, no solving of an optimization problem. They're simple analytical expressions that we can plug in. Even I can code that up and put them together and calculate the derivatives of the endpoint, provided we have these first derivatives here, which depend upon the problem. We can put those together and get those derivatives. And just to show that that's working, here's that same example again. This is going to be our starting point, our blue waveform. The orange is going to be our target observed waveform. You can see it's off in time, it's off in amplitude, and of course it's off in frequency. And here, I'm going to play an animation. This is the Wasserstein distance as a function of iteration, and this one's going to be the equivalent least squares of the same model. So this is the path it's taking in the multi-minimid surface. But this is the one it's actually taking, because this is the one we're optimizing. And here we'll see how this one goes to fit this one. So we'll play it across, and what happens is, well, it's very quick, I realize that. It should play again. Okay, so what happens first is, all we're doing is rolling down this quadratic surface, but in terms of the fitting, the first thing that happens is the two waveforms line up. The second thing that happens is that their frequencies align, and the third thing is that the amplitudes align. And that's very interesting, I think, because when people want to fit waveforms or want to fit surface waves, the first thing they do manually is to try and align the envelopes, to try and align the energy, because we know that that's the best thing to do, to try and fit the waveforms. What happens is this Wasserstein distance does that automatically, because that's where the biggest bang for buck is. Of course it is. That's what would happen if you could turn this into a globally quadratic surface, and that's what we're doing. So it fits the shift first, then it fits the frequencies, and then it fits the amplitudes. And you can see here that we're jumping over minima to global minima. So the least squares is getting bigger. That's because on the other surface it's jumping over them, whereas this one is going down uniformly. Okay, so I'm always telling my students, you can't present one result, everyone thinks it's a special case. We'll just do another one just for fun, because we've got time. Here's a starting problem where the initial wavefront has too high an amplitude, it has too high a period, too low a frequency, and it's shifted again. And we'll play the same thing again. Again, it fits the time shift first, and then it sort of does the amplitude and the frequencies together. Okay. So why do I think this is useful for the future? And it's because that this simple idea fits together, and we've produced a globally quadratic surface. Now that's music to the ears of anyone who fits waveforms. This is a very simple example. It's not yet clear that it will translate into more complex problems, but I am hopeful, with the fingers crossed, that it will. So again, this is for the students and the postdocs. that this is an interesting area that we could get into. These things fit together like a piece of jigsaw and produce a sort of system that seems to work. Okay, so my biased conclusions from my biased tour. There remain unexplored applications of sparsity. Busa is experimenting with overcomplete tomography. There are other potential applications of that. I've really just given you a taster of that, but I think it's a step beyond what we can currently do with this concept, and we can generalize it. That's the idea. When machine learning obviously has great potential in inversion, I think everyone recognizes that. The real challenge is how do you actually make use of it? And we're suggesting it's a surrogate for forward and inverse problems. Particularly, it could be used to replace or enhance Markov chain Monte Carlo or directly address nonlinear problems. Both of these are works in progress. There is potential. It's not the end of the story. That's why there's lots of opportunities to get into these fields. That's why we're forward-looking here. And I think building on the excellent work done in optimal transport, I think this is an exciting area. I mean, Andy Jackson got me into this, and I've not been able to think of much since, because I've always wanted to find a way of properly doing inversion. And I think this might be that proper way of doing them. And as always, these tools exist. These ideas exist, these little phenomena exist, and really the challenge for a geoscientist, and particularly the next generation, is to sort of be innovative in how you pose, how you bring these tools together. It's not plug and play. In all of these cases, it's a case of how you pose the question and how you might utilize these capabilities. And that's always been the challenge, I think. So I will finish with one last thank you and a comment on my life tour guides as opposed to my work tour guides. Those are the 4 people there. They're sitting in the audience. Without them, I wouldn't be here. They don't look like that anymore, but I think they look like that in my head. But I did say I was biased. Thank you.